When you type Docker run, Docker does not actually create your container. Instead, it sends a request to another program that is already running quietly in the background. That program hands the work to another one, which hands it to yet another, and that final program is the one that actually creates your container. By the time your application starts, the program that created it is already gone. Podman reaches the exact same result, but it takes a completely different path. There is no background manager waiting for requests at all. In this video, we will follow one container from the moment you type Docker run or Podman run, all the way until your application is running, and by the end you will know exactly what happens behind the scenes, why Docker and Podman feel so similar, and when you should choose one over the other. Before comparing Docker and Podman, we need a much simpler answer. What actually is a container? Surprisingly, Linux itself has no such thing. There is no create container instruction, and the kernel has no built-in container object. A container is simply a normal Linux process, made private and limited by three technologies working together. First, a set of kernel features called namespaces isolate what the process can see, giving it its own process tree, its own network, its own file system view, and its own hostname. Second, another kernel feature called cgroups controls what the process can use, limiting things like CPU time and memory. Third, a layered file system means Linux does not copy a whole operating system for every container. Instead, it stacks a few read-only layers underneath one readable layer. That is the entire idea. A container is just a Linux process wearing those three technologies like a disguise. Throughout this video, we will follow one small web service image called API version 1. Once that application is running, it does not matter whether Docker started it or Podman started it. At that point, they are running the exact same Linux process. The only difference is how each tool gets you there. Start with Docker. The Docker command you type in your terminal is only a client, a remote control. It does not build containers itself. Instead, it sends a request over a local connection to a service that has already been running in the background, usually since your computer booted, called Dockered. Think of Dockered as Docker's always-on manager. It keeps track of downloaded images, networks, and volumes, and it answers Docker's API, but even Docker does not create containers directly. It asks a second background service called Containered to do it. Containered's job is managing each container's lifecycle, start it, stop it, watch it. Containered then launches a small helper program called a shim, one per container, and the shim starts the program that actually talks to the Linux kernel, called runts. Runc reads a configuration file, creates the namespaces and keygroups we just described, mounts the file system, starts your application, and then immediately exits. That exit matters. Runc only sets the stage. It is never part of your running container. Once your application starts, the shim stays behind to watch it while runts disappears. So one Docker run command actually relays through 5 separate programs before your application ever begins running. If you inspect the process tree afterward, something interesting shows up. Your application is not a child of your terminal anymore. It is attached to the shim. The shim belongs to Containered. Containered belongs to Dockered. Your terminal simply started the chain, then exited and stepped away. This design has real advantages. Because Dockered is always running, it can restart containers automatically, expose an API for tools like Docker Compose, and manage every container on the machine from one place. But there is a trade-off too. One background manager is now responsible for almost everything. Years ago, restarting Dockered could stop every container on the host all at once. Docker later added a feature called Live Restore to reduce that risk, but it still depends on the manager coming back healthy. Docker's whole architecture revolves around that one central manager. Podman starts from a different question entirely. What if there was no central manager at all? When you run Podman run, there is no background service waiting for the request. The Podman command performs the setup itself in that single moment. It prepares storage, it configures networking, and then it starts a lightweight watcher called conmon. Conmon launches a runtime, usually one called crun, which creates the exact same namespaces, cgroups, and file system that runts would have created. Once your application starts, crun exits, and then Podman itself exits too. The only process left behind is conmon, and its only job is to watch the container, collect its output, and report when it eventually exits. If you close your terminal, the container keeps running anyway, because conmon has already been adopted by Systemd, the normal service manager already running on your Linux machine. There was never a background manager involved at any point. At this point, you might expect Docker and Podman to produce different kinds of containers. They do not. Both follow a shared standard called the Open Container Initiative, or OCI. OCI defines three things: how container images are packaged, how a runtime like run or cron should start a container, and how images are pushed to and pulled from a registry. Because Docker and Podman both follow those rules, an image built with Docker runs perfectly on Podman, and the reverse is true too. Even the runtimes underneath are interchangeable. Docker can be configured to use cron, and Podman can be configured to use runc. The container itself, that plain Linux process from before, is identical either way. The real difference between these tools is everything layered above the runtime. Docker's biggest security discussion is not really about containers at all. It is about the manager. By default, Docker runs as root, the most powerful account on a Linux machine. That means anyone who can talk to Docker's socket, the local connection the Docker client uses, can effectively control the whole machine. They could, for example, ask Docker to mount the host's real file system inside a container. In practice, access to that socket is almost the same thing as having root access, and plenty of CI pipelines hand it out without thinking twice. Podman was designed around a different default. An ordinary user can create containers without needing a root-owned manager anywhere in the picture. Inside the container, the process still believes it is running as root, but the kernel quietly maps that root back to your own unprivileged account on the host. If the container ever escapes, it does not become the host's root user. It becomes you. Networking follows the same pattern we have seen all along. Both tools ultimately build the same kind of virtual network for your containers. The difference is simply who is allowed to configure it. With root, Docker builds a bridge called Docker 0 and opens ports by programming the host's firewall directly through Dockered. Podman builds the same shape using its own tools, Netavark and Aardvark, a network backend paired with a small DNS server, so containers on the same network can find each other by name. Take root away, and the physics change. Neither tool is allowed to touch the host firewall or create a bridge without it, so traffic instead flows through a small forwarder running in user space. That extra hop is real overhead, and it is the strongest argument for keeping root on a busy Linux server. If you have used Kubernetes, you have probably heard of a pod, a small group of containers that share a network and storage. Podman borrows exactly that idea, right there in its name, Pod Manager. You can group containers into a pod locally, and Podman generate kube turns that pod straight into Kubernetes YAML. Supervision follows the same philosophy. Rather than build its own restart logic, Podman hands that job to the init system already running on your machine. A small quadlet file describes your container using system's own syntax, and system pulls it, starts it, restarts it if it dies, and orders it against every other service on the box. Kubernetes itself, notably, runs neither Docker nor Podman directly. Its nodes talk to Containered, the same lifecycle manager from Docker's stack running on its own, or to a minimal runtime called CRI-O, which shares its underlying libraries with Podman. Building images splits along the same line. BuildKit is simply Docker's modern image builder, not a separate container runtime, and Docker build hands your Docker file to it. BuildKit runs as its own background service and adds real parallelism and shared caching. Podman build instead uses Buildah, a tool that builds the same kind of OCI image with no background service at all. For most teams, the speed difference between the two is noise, next to how well you have configured your cache. The gap that actually matters shows up in CI, where building with Docker usually means mounting that root-owned socket, or running Docker inside Docker with full privileges. Buildah builds unprivileged inside a plain ordinary container the whole time. So why does Docker still dominate? Gravity. A decade of tutorials, Stack Overflow answers, and CI templates all assume it. Compose is the sharpest edge of that gravity. Podman now exposes a Docker-compatible socket, and the official Docker Compose tool can run against it directly, but you will still meet Compose files and tools like test containers that assume the real Docker socket specifically. Most projects work without changes, but you will occasionally run into tools that expect Docker by name, and when that happens, expect some extra debugging. Here is the recommendation I would give most teams today. On Linux servers you control, use Podman. For security-sensitive CI pipelines, use Podman or Buildah. For Mac and Windows development, stick with Docker Desktop if your team already lives there, or reach for Podman Machine, a solid free alternative if you are starting fresh. For teams already built around Docker Compose, stay with Docker unless you have a genuinely compelling reason to switch. The nice part is that your container images stay OCI compatible no matter which tool built them, so switching later is far easier than most people expect. Docker and Podman are not competing container formats. They are two different ways of managing the exact same Linux primitives, namespaces, C groups, in a process that is, underneath everything, just a process. Once you understand the chain of programs behind Docker run, containers stop feeling like magic, and that habit, tracing what actually runs the thing you asked for, is worth carrying into every piece of infrastructure you learn next. The best engineers do not just know which command to type. They know which process is actually doing the work. If this sharpened that mental model, like and subscribe for the next deep dive.